Let's go over one of the questions from the homework. This is 5.9. The homework it was a classwork, and then you're going to do problem set 7 through 11 at home, and then this is problem 7B. We went over 7A in class, and I'm going to write this down. If you don't have to write this down, but the process might be good for you all to do this, and we're going to use the technique called log differentiation. I'm hoping that I write this down correctly. Oops, this is a 5. There's going to be a lot of fractions in here, and one of the things you have to remember is the idea of log properties. So if we move to here, we have these log properties. If the argument is being multiplied, then you can break them up into 2 terms, each with log of the same base. This works with ln as well. Even though this says log, you can also do this with natural log. The division rule is when you have, remember, if you divide inside the parentheses, you can subtract logs on the outside. So if you want to pause this video so you can write this down to remember it, that's fine. I literally just Googled log properties and looked for something that looked familiar. If you did not know change of base, it's something that you can stare at this until it makes sense, but this was used because calculators couldn't do different bases, and this is useful for calculator if you don't have the log base function. Most of you do on your TI-84s, so you don't have to worry about that. But I'm going to be using all 3 of these properties, the product rule, division rule, and power rule. So if you want to pause this to write this down, and then the next questions may make more sense. So the process that we are going to use is called logarithmic differentiation. Similar that we have a technique called implicit differentiation. And then usually when we do differentiation, we already know the product rule, the quotient rule, the power rule, but sometimes it's not enough for us to take derivatives. So we turn to things like implicit differentiation, or we turn to things like log differentiation. So what this means is we're going to take the natural log of both sides, because in calculus, I use the natural log. But first, what I'm going to do, I almost always rewrite my radicals with a fraction exponent. I find that helpful for me. So x minus 3. So here's where the fractions start coming up, which may be difficult to keep track of if you aren't sure where they come from. This 1/5 is me rewriting the radical square root of 5 as a fraction exponent. Now what I'm going to do is I'm going to take the log of both sides. And when I log, I use the natural log because, boo, log base 10. It's all about natural log with base e, woo. I come from a science background, and then you'll find in calculus more and more you guys use natural log. Okay, so far this is the same. I'm going to use my power rule, where if you have an exponent, you can bring it to the front and multiply that power by log. You see this? I'm going to bring this over to the front. So I'm going to rewrite ln of y is equal to 1/5 ln of this big everything here. Do you have to write this down again? Yes, you do. There's no way around it yet. Okay, now inside of here, I am going to use my division property. I have a numerator and denominator, so I'm going to write 1/3 in these big old brackets, and I'm going to rewrite ln of times x squared plus 1 minus ln of 2x plus 5 to the 3rd. Okay, big brackets. Now I'm going to use my product rule because there's a product in this argument. Just like x and y are products, I'm going to split them up into 2 logs. So ln of y, big brackets, ln of x minus 3 to the 4th plus ln of x squared plus 1 minus ln of 2x plus 5 to the 3rd. Big closing brackets. So, now what this allows me to do is I can now take using implicit differentiation. We just did log differentiation, which we're doing the process of, and part of log differentiation is implicit differentiation. What I'm going to do is I'm going to distribute this 1/3 just to break off my brackets. Okay, so I'm going to scroll down. ln of y is equal to 1/3 ln. I'm not skipping any steps here, even though there are plenty of times where you can combine steps. I'm just not going to do that right here because I want you to see all my steps. Oh, I wrote that wrong. Okay. Okay, now what I'm going to do is I'm going to use the power rule on my right-hand side of the equation. I'm going to use my power rule and take the power and multiply it by the log. So this 4, I'm going to multiply here. This is nothing, so I'm not going to multiply it. And this 3, I'm going to multiply it here as well. Did I write something wrong? Oh, this all says 1/3. This should say 1/5. 1/5. 1/5. I don't know why I wrote 1/3, but that is very confusing. Okay, that should all be 1/5. Wow, you guys must have been so confused. I bet some of you were like, I hope she catches that because it's going to change everything and it's all going to be wrong. Okay, so again, I'm going to multiply my 4 times I'm going to use my power rule for logs, and I'm going to bring down the powers. And this technique is good because it actually saves you a step for a chain rule. You could just do it the long way, but you're pretty much forced to do it this way. Now I'm going to do my implicit differentiation. So the derivative of ln of y is 1 over y, because the derivative of ln to anything is 1 over that argument. Now, because we are actually supposed to find dy over dx with respect to x, we have to use the chain rule there. So now this, I'm going to take the derivative 4/5, which is a constant, and I have to use the chain rule. So I'm going to do 1 over my argument times the derivative of my argument, which is just 1. Luckily, it doesn't change anything. So from this line to this line, I took the derivative. If you were to do it in your scratch work on the side and just do every derivative on its own, you would get this answer. And I'm going to do it all in one line because I'm a pro like that. Okay, so 1/5 times the derivative of log of an argument is 1 over that argument times the derivative of the inside. So my 2x is coming from the derivative of my inside. That's my chain rule. Okay, I'm going to do the same thing over here. 1 over 2x plus 5 times the derivative of my inside function, which is 2. So this problem practices a lot of derivative rules, implicit differentiation, and log differentiation. So you can see why teachers like this problem. Let's just keep simplifying it. The only thing I have to do now is multiply both sides by y. That should be in the numerator. So I'm going to write dy dx is equal to, I guess I can combine this, 4 over 5 times x minus 3 plus 2x over 5x squared plus 1 minus, I'm going to combine this, 6 over 5 times 2x plus 5. Am I on my way? Yeah. And all of this is multiplied by y. Instead of y, I'm just going to write in what y is. And you have to go back to the very beginning of the problem. All of this is y. So you just take this big chunk, this structure, and go plug it back into here. X minus 3 to the 4th, x squared plus 1 over 2x plus 5 to the 3rd power. Okay? So this whole answer is your derivative. Let's recap. We weren't able to take the derivative of this. We want to practice with log differentiation, taking the derivative of this. So we logged both sides to practice log differentiation. We got to a certain point after we did some algebra where we had to use implicit differentiation starting at this line right here, implicit differentiation. After the implicit differentiation, we had to use log the derivative of our logs rule, and then at the end you have to multiply both sides by y and substitute in what y is. That was the summary of this. This whole thing is your answer. Best of luck. Goodbye, people.